Yay, it's working. Okay. Okay, folks. So the plan for today is to discuss time-dependent perturbation theory. All right. Did you hear that okay? Is everything good? Thumbs up? Okay. So, all right. So that's the plan for today. And this is a new topic, and it's a big new topic. It's a very important, big new topic. And so basically, we want to look to see how things change with time. And you've already done that in quantum mechanics. I just want to remind you, you have already been thinking about time, at least last semester you thought about it. And so I just want to remind you that you guys remember that if I have, you know, that if we have some Hamiltonian, and we have some Hamiltonian that acts on these eigenstates, then you guys know that if my wave function at time t equals 0, if I know my wave function at time t equals 0, then you know that the wave function at some later time is equal to just a sum over all the eigenstates weighted by this weighting factor, where this is the wave function at time t equals 0, and then you have these time-dependent phase factors. Okay, so you guys all know this. Like if you already knew the wave function at time t equals 0, then you basically just expand into the eigenstates. In this familiar way. So this I'm hoping that this is, you know, looking kind of familiar to you. And then you derive this. Remember last time you derived this last semester from the time-dependent Schrodinger equation, the time-dependent Schrodinger equation. And I'll remind you of that. It's just this: h psi equals I h bar d dt psi. And then from this, you derive this expression using our old friend, separation of variables. And in this case, the variables were position and time. Okay, so I'm just reminding you that. So this is what you've done. This is what you know or should know, or you know, it should look familiar. You know, maybe you should go and review it if it doesn't look familiar. But here's the thing. You know, what if separation of variables doesn't work? And it doesn't always work. In other words, when you did this derivation, then you assumed here that the Hamiltonian does not equal a function of time. And you might not even remember that when you did the derivation. I mean, you probably don't, because you know it's like last year sometime. But that's what you did. To do this step from here to here, you assume that the Hamiltonian is not depending on time, that it's constant. And then you can do your separation of variables trick. But it turns out that separation of variables often does not work. We often have that the Hamiltonian depends on time. And then the trick doesn't work. Separation of variables doesn't work. And so your simple intuition from last semester goes into the garbage can. So if the Hamiltonian is time dependent, then simple picture falls apart. And I just want to emphasize that, you know, the simple picture doesn't always work if the Hamiltonian is not constant. And this is very common. So the h equals a function of time all the time, because the world is not static. I'll just write that, you know, our world is not static. And so you know that things change all the time. And so the idea that the Hamiltonian is a constant is, you know, pretty stupid. You know, it's like, come on, give me a break. Of course it's not a constant, you know, but we make it a constant because it simplifies the picture, and, you know, it's an approximation. You know, we often say that h equals constant because it's a good approximation. But you know that in the real world, things are changing all the time, and so you know, we need to deal with that. So so let's give an example of a Hamiltonian where the Hamiltonian is changing with time. There's many examples, many famous examples, but let's give one that you've seen before and that you think you understand, or you understand a little bit. Let's consider this example. Let's take an atom, and it has energy levels, you know, like a hydrogen atom. Okay, that's how I draw an atom, just like a little box, and it has these levels: E1, E2, E3, etc., and then more levels up here, and then these have states associated with them, the eigenstates phi1, phi2, phi3. Okay, so those are the eigenenergies and eigenstates of some random atom. Now suppose that the electron in that atom is sitting here in the ground state. Now I shine a light on it. There's a little man. The little man has a laser or a flashlight, and he's shining light. He's wearing a hat with a nose, and he's shining light onto the atom. And this happens all the time. I mean, anyone, you know, who's used a flashlight has done this, right? And so so suppose that h bar omega is equal to E2 minus E1. Then somebody tell me what happens.
It transitions up to the E2 level?
Yeah, exactly. Then transitions up to E2. Yeah, that's exactly right. But here, now I'll ask you a question. What's the probability that that happens? Suppose the little man has a flashlight with a certain strength of light, and he shines the light for, I don't know, 72.6 microseconds. What is the probability that the atom will transition into that upper state? Now, can anybody answer that question? And of course, the answer is no, unless you've already taken this class. You know, it's a trick question. So, you know, you're not supposed to be able to answer that question. That's the whole point. That's what after this class, you should be able to answer that. I mean, after this course, you should be able to answer that question. But I want you to understand that, you know, you guys have seen this before, you know, in some other class. But the question becomes like, how does it happen? You know, how does this work? Why does it happen? Why does it happen? And you know, I know that you guys have never really stopped to think about it, probably, because, you know, it's like a simple picture. Okay, I got that energy and it jumps up there, but really, why does it happen? And it's not completely obvious, because if you look at it, you remember that, you know, phi 1 is an eigenstate, meaning that h phi 1 is equal to E1 phi 1. And that means that phi 1 should be, get this, that means that phi 1 should be a stationary state. And stationary means unchanging. And so phi 1 is a stationary state. That means it does not change in time, other than just a phase factor, that you know, the phase that's spinning, but it should not really change in time. And yet it does. When I shine light on it, I get a transition, you know. And so already you can see, you know, something's happening, you know, you know, something funny is happening. And so that's what we want to understand, you know, what happens. And so basically what's happening is, that the flashlight, what's happening is that the laser is changing H to a time-dependent Hamiltonian. So, and before the laser, then I had H equals a constant. What was the Hamiltonian before the laser turns on? Somebody tell me.
It was just the particle in a box Hamiltonian.
Right, which is the nucleus. You know, it was just the proton, the nucleus pulling the electron towards it, the Coulomb potential. That's right, which I call a box. That's right. But after the laser turns on, while the laser's on, maybe I shouldn't say after, I should say during the time of the laser, I have that the H is equal to a function of time. Because the laser, you know, is a function, has the electric field is a function of time. And that makes sense, because, you know, if this is a laser and it's sending out a light wave, then you guys know what a light wave is that a light wave is this. You know, here's my atom, you know, with my energy levels, and then but the light wave is this thing where I have, I mean, what is a light wave? A light wave is this. I have an electric field here, and here, and here, and here, and I also have a magnetic field, D, and here it's pointing into the board, B, and here it's coming at you. Okay, so this is a light wave, right? So a light wave is this traveling electromagnetic wave, And so you can see that the electric field, you know, there's electric field that hits this atom, and the electric field is going to be a function of time. There's also a B field too, because an electromagnetic wave is this electric field and B field that travels through space, and when it hits that atom, the atom is going to see an electric field that very rapidly goes up and down and up and down. Okay, and so obviously this is going to cause my Hamiltonian to change in time. There's no tricks here, you know, it's just common sense. If the electric field, you know, the atom used to be just sitting there all stationary and unchanging, but then this electric field is going up and down and up and down, and so clearly you know, the Hamiltonian is changing with time. So then the question is, how do we understand it? If the Hamiltonian is changing with time, then how do we calculate? How do we calculate probabilities anymore? How do we do quantum mechanics, basically? How do we calculate probabilities? Because everything kind of falls apart. All of the approximations that you've made previously all fall apart. And so it's not obvious how to do it. You know, the answer is not obvious, I think, to me at least. I mean, unless you're some kind of genius. But for most people, the answer is not obvious. But it turns out, even though the answer is not obvious, the answer is simple. I mean, simple things are not always obvious, but that doesn't stop them from being simple. The answer is simple. You just solve the Schrodinger equation, like everything else. You just solve the Schrodinger equation. And the Schrodinger equation is this. Before you had H psi equals IH bar ddt psi. And the thing is, this still works. It still works when H is a function of time. Okay? So the idea is, I just want to say right up front, the Schrodinger equation still works. Thank God. Otherwise, we wouldn't know what to do. It still works. And so this is the Schrodinger equation now. Now we have H of t times psi of xt is, actually, I'm going to write it somewhere else. Too much there. We have H of t times psi of xt is equal to IH bar d dt psi of xt. Okay, so this is what we have to solve. And if you solve that, then everything works and you can figure everything out. Okay, you can figure everything out, because what you would say is you would have boundary conditions. You might say that my atom at t equals 0 is in some eigenstate. Okay, that's an eigenstate. And then I might say my Hamiltonian at t then I might say that you could say for t less than 0, then my Hamiltonian is constant, h naught, and I could say for t greater than 0, I turn on my Hamiltonian is now time dependent. Okay, so that's what you do, and then you have boundary conditions, and then so then what you do is you solve. In physics, we know what to do. If someone gives you a big ugly differential equation, you know that you solve the differential equation and you plug in the boundary conditions. And then you just get the answer. So that's sort of a general prescription, and that works. But the problem is that it's too hard. Just plugging in plugging into this differential equation, the time-dependent Schrodinger equation, and then just grinding through the differential equation and then plugging in the boundary conditions and doing it exactly, it's just too hard. It's like, it's this big nightmare. I mean, people do it, of course, who have computers and are theorists and, spend their lives doing it. But for most people, it's just too hard. It's just a big, complicated mess. And so we want to know, how do we think about it? How can we understand it in an intuitive way? And how can we boil it down to just some very simple recipes, some simple formulas and recipes that allow us to solve physics problems without too much difficulty? Because that's what we like, because we're lazy. Everyone is lazy and nobody wants to work harder than they have to. I know I am. So nobody wants to do more than they have to. and so what we do is, to make it simpler, is we use perturbation theory. And you can already see how, so we use perturbation theory, and you can already see how the perturbation theory might rear its ugly head, because the idea is, if at t less than 0, my Hamiltonian is some simple Hamiltonian, like let's say a hydrogen atom Hamiltonian, hydrogen atom, then if I turn on my laser, I shine light on it, turn on the laser at t greater at t, if I turn on my laser at t equals 0, then for t greater than 0, what we would say is h is equal to h naught plus the Hamiltonian, the change, the new Hamiltonian, the perturbation, which is due to the laser. So that's the perturbation due to the laser. And so you can see how we can formulate time-dependent problems in this framework of perturbation theory. I just sort of want you to see that there's a very natural framework, and you guys already have experience with this perturbation theory, and so you can already kind of get a sense of where we're going to go with this. We're going to start with our unperturbed states, and then we're going to turn on the perturbation. Okay, and that's how we're going to understand how things change in time. That's how everybody understands it. That's how, like, normal people who use quantum mechanics all the time, when you're thinking, okay, how do I understand these time dependent processes? Because there's no real stationary states anymore. And how do I understand it? Oh my God, it's so hard. It's just a big nightmare. But what we do is we think in our brains in terms of perturbation theory. And so perturbation, and before, when I told you about perturbation theory, I've said this to you before. I don't know if you completely appreciate it, but one of the points of perturbation theory is that perturbation theory, first and foremost, is a way to calculate things. We calculate stuff with perturbation theory, and we've already done that. You just had the midterm and you had to calculate all this stuff using perturbation theory, so you understand that. But second, and very important, is that perturbation theory gives us an intellectual framework to understand how nature works, because just most of us are unable to solve the Schrodinger equation in our head. It's this differential equation, and most of us are not smart enough to just solve it in our head for every situation. And so we need simple frameworks, because we're just simple humans, we're just animals, our brains are not too big. And so we need things to be a little simpler. And so perturbation provides us with a simpler picture that we can sort of understand things. It provides us with a physical picture. And I want you to appreciate that, that perturbation theory is not just a calculational technique, but it's a whole framework for visualizing how quantum mechanics works. So let's think about it for a second. Like here, for example, let's think of, let me just kind of give you a sense of what I'm talking about. I mean, so if before the laser is turned on, before laser, I have my atom is just sitting in some eigenstates, you know, with their energies. And it's happily sitting in an eigenstate. Then what happens after I shine my laser, then there's some probability that I have a transition, that I go from this state to this state. And this is my phi 1, E1, phi 2, E2, phi 3, E3. Now, that's sort of how we think about it. That's you were even taught this picture, but I want you to appreciate that what you were thinking and what you were taught is already perturbation theory, because the way we visualize it in our mind is we have these are the unperturbed states, and we go from one unperturbed state and we transition to a second unperturbed state. So this is a transition, you know, from here to here. That's a transition. So you see how the light that hits the atom is causing a transition from one unperturbed state to the other. So that to even consider that the electron is jumping from one state to the other, the states that we're talking about are the unperturbed states. But you have to understand that this picture is already using perturbation theory, because in reality, the unperturbed state, there are no unperturbed states. You know, when the laser is turned on and the electric field is hitting the atom, the old Hamiltonian is gone. I have a new Hamiltonian. And so these states are no longer eigenstates. You know, there are, so when you even think of transition from one state to another, you know, you're thinking in your head, I'm going from one eigenstate to another, but those states are no longer eigenstates when the laser is on. And so really that picture to say that the electron is transitioning from one state to another, that we're already using the perturbation theory, because we're using approximations. We're basically saying, well, you know, the laser is on, and so those old atomic states, they really aren't eigenstates anymore. The new atomic states are some really incredibly complex states, and I'm really making transitions between the new eigenstates. But the new eigenstates are just this horrific, complex mess that I can't even understand how to visualize. And so I'll just discard all of that complexity, and I'll just think in terms of the old states, the old states. And that's sort of using perturbation theory already. And that's what we do. But I do want you to appreciate that what's really happening is that what's really happening is that when you know, what's really happening is that the light is causing the old states. What's really happening is that you're sitting in some old states, and then you have the light, you turn on the light, and then you get some new states. I'll call them phi 1 twiddle, phi 2 twiddle, phi 3 twiddle. And so these are the new eigenstates. And these are the new eigenstates that solve the new Schrodinger equation, you know, when H is equal to H of T. And what's really happening is that you're making transitions. What's really happening is that you have your wave function can be written as some linear superposition of the new eigenstates, where I have the new phi n twiddle, and you have your original eigenstate here, which is psi at x t equals 0. And so you have to overlap that onto the new eigenstates, and they are evolving in time according to their new energies. And so this old idea still works, but you're transitioning, you're evolving in time because you're no longer in a true eigenstate anymore. You're in an admixture, and so this causes you to have that's what causes transitions. The fact that you're no longer, that your old state used to be an eigenstate, used to be a stationary state, and is no longer stationary. Okay, so if that didn't make sense, or then let's not worry about it, because we're gonna go through the prescription. I just wanted to give you some kind of overview of that, but we're gonna go through the prescription very in great detail. And so the question then is, so let's so far this has been an abstract discussion, but let's make it more like let's consider the most important example. The most important example of time-dependent of this phenomena is light. So I'm going to use the idea of shining light on an atom as the problem that we want to understand the most for time-dependent processes. And but this could really apply to any process. It doesn't have to be light. I'm just using this as a concrete example of a time-dependent quantum mechanical process, but it really could be anything. I mean, I could turn on gravity. I could turn on some pure force. I could do, there are other things that we can do. Okay, but so let's solve it. Let's solve this problem. This is the problem that I want us to solve. I'm sitting in some state at t less than 0, and I'm sitting in some state, I'll call it the kth state, some random state, and I shine, and then I shine some light on it, at t equals 0, turn on laser, and then at t greater than 0, I want to know what's the probability that I have made a transition to some other random state. At t greater than 0, what is probability to be in state M? So we start in state K. Okay, this is the problem I want us to solve. So this is a well-defined quantum mechanics problem. We started in state K at t less than 0. At t equals 0, I turn on the laser, which has some frequency h bar omega, some electric field that's oscillating in time with frequency omega. It hits the atom at t equals 0, and at some time later, and let's say I left the laser on. So lasers, let's leave the laser on. Laser stays on. Then the question is, at some later time, what's the probability that I find my system transitioned to some new state? All right, so that's a well-defined problem.
Professor?
Yeah.
So in reality, when the light is shined on the particle and it transitions, it's not going to be another eigenstate, but we're treating it as it is another
Yeah, because the other states are no longer true eigenstates. Because what is an eigenstate? An eigenstate is this, H psi equals E psi, right? That's an eigenstate.
Yeah, and then the
This
Hamiltonian.
goes out the window, right?
Yeah. Okay, got it.
That's right. And so, yeah, but we're going to pretend that it's still we're going to pretend that the eigenstates still have meaning, and they do have meaning. They do, because it's sort of like that's like what you've done up to now. We've been talking about perturbation theory. We've been talking about the unperturbed states and the perturbation, and what's the energy now, how do the energies shift and this and that. But we're doing everything. We're using the unperturbed states as like our framework, and the reason is because we understand the unperturbed states. They make sense to us, and so we need to grab onto that like what do you call it, like a safety jacket, like we're drowning and we need to grab onto something to stop us from drowning. So we grab onto those unperturbed states. And that's it's not just a psychological prop. I mean, it really is, even physically, if as long as the perturbation is weak and short, the unperturbed states are still mostly okay. All right. And that will make more sense as time goes on. Okay. All right. So we got to solve this problem. And so how do we do it? Then, what do we do? What do we do? How do you solve this problem? All right. It's not obvious at all. I mean, it's simple, but not obvious. Different things. So, okay. So basically what we have to do is we have to solve this. Basically, you just solve the Schrodinger equation. H psi is equal to I H bar d dt psi. All right, that's the Schrodinger equation. So that's what we got to do. And it's not, so that still works. And so, but the problem is that now H is a function of time. So we have to solve this problem, which is kind of a pretty hard problem. Okay, so that's what we got to do. And so the question then becomes, how do we do that? So, well, what's the first thing we got to do? Somebody tell me. This is what we got to solve, okay?
Assume psi is separable in x and t.
That is a smart thing to try. That's the separation of variables, and that's what you did last semester to solve this problem. But that only works when H is constant. So that's not going to work now. At least it's not going to work. We can't use separation of variables as easily as we did before. Well, we will sort of use it, but what's another thing that we should? But we'll do something like that. But before we even solve this equation, do we know all the terms in this equation? What is it that we're missing?
The Hamiltonian?
Yeah. So let's start with the Hamiltonian, and then we can start making assumptions on the structure of the wave function. So we will do something like what you said, like separation of variables. So the first thing a good place to start is the Hamiltonian. And so I could just leave this as a completely, we can just leave it as a completely abstract Hamiltonian, and we could just say, H equals H of t, just some arbitrary time-dependent Hamiltonian. But I want it to be a little bit more tangible than that. Let's actually calculate what the time-dependent Hamiltonian is. And so for light, so if we're shining light on something, then here's my light wave hitting something, hitting an atom. Here's an atom, with its energy levels. Then the question is, what is the Hamiltonian for that? And so it turns out that the right way to do it, it's kind of complicated, because we have an electric field and a B field that are changing in time. They have a time dependence to them. And so basically this is the right way to do it, and then I'll make a big approximation. So the correct way is to use the vector potential A, which is related to the electric field and B field, because you guys remember that the B field is equal to the curl of A, and the electric field is equal to the time rate of change of A minus the gradient in phi. We also can have this. And so if we have a vector potential, then what we can do is we can say that the Hamiltonian for an electromagnetic field, which is a function of time, can be written like this. We have the momentum minus the charge. If there's a charged particle in here, like an electron, we have the charge on the electron times the vector potential squared over 2m plus q times phi plus, well, we'll just stop there. Okay, so this is the Hamiltonian for an electromagnetic field, for a charged particle in an electromagnetic field. And so often in quantum mechanics problems, you will see the vector potential. The vector potential plays a big role in quantum mechanics. A equals vector potential. So I just want to say that, because it's true. The vector potential is really important. It's a really funny thing that when you learn electricity and magnetism, the vector potential is there, but it's sort of not that important really compared to the actual scalar potential. And you don't use it all that much, but in quantum mechanics, we use it all the time because the vector potential is sitting right there in the Hamiltonian, okay? So to really do electricity and magnetism correctly in ENM, we need the vector potential. But for today, this is too hard. And so we want to do it easier. Because 99% of the time, we only need the electric field. Okay, and so I just want to say that, like, for an electromagnetic wave, it has an E field and a B field, and they're changing in time in this complicated way. And to do everything correctly, you have to use the vector potential. But for most of the time, we can get away with a much simpler formulation. So the simpler formulation works 99% of the time. And so this is what we'll do in this class. The simpler formulation is that we have, we know that if I have, if we know that if I have an E field, an electromagnetic wave has an E field that's coming in, and I know that, and I have my atom, and I have my charged particle, the electron, which is sitting in that atom, and the charged particle feels the electric field. And we know that what it feels is a force. And this is a classical discussion. Remember, we always use classical mechanics to get the Hamiltonian. That's where you always start with classical mechanics. And so we know that there's a force that charge feels, which is Q times E. And we know that force is equal to a gradient in some potential. I'll call it U, or I could call it V. I'll call it U. And so then we know then that U is then going to be equal to the negative of the integral, because I can, I can integrate both sides. So integrate both sides, and then we get that U is equal to negative Q E dot dr from 0. We do all these things correctly. So then this would be u of r. Okay, so this you've done before in some class. I know you've done this before. So if I have some, because if I have some force, then I just can, you know, integrate both sides to get the potential, and I have that little negative sign, which is so annoying. It makes everything a little more complicated, but it's not so bad. And so then you see that if then what we can do is we can just say, let's just say that if E is constant, here's the thing. An atom is small. Atom is small. And so if the wavelength of the light is giant, that's the wavelength of the light. But if the atom is tiny, there's my tiny atom with its energy levels, then over the distance of the atom, the size, delta x of the atom, then I can say that the E field is constant in space. It's not constant in time, but it's constant in space. Do you see that? For small things or small atoms. Can somebody tell me, to justify this approximation, can somebody tell me what is the wavelength of optical light?
Like 600 nanometers or something?
That's right. Let's say 500. So lambda equals 500 nanometers. That's 5,000 angstroms for let's say green light. And what is the size of an atom?
An angstrom.
Exactly. 1 angstrom. So this approximation is quite good. All right, for most things, this approximation is great. So that means that if if the electric field is constant in space, then that means that I have u of r is equal to this integral. But when I integrate it in space, then it's just going to be q e dot r. So simple. All right. And so that's our Hamiltonian. So this is really, isn't that easier than all those vector potentials and stuff? So it's so simple. And so then we have for light, what, you know, so for light we have that the electric field is equal to some E naught you know, for a real electromagnetic wave, it looks like this: sine of k dot r minus omega t. You know, that's an actual electromagnetic wave. Okay, that's a wave, an EM wave. But what we're assuming is that that's a general electromagnetic wave, a plane wave. But if the atom is small, then what the atom sees, if the atom is small, then let's assume that the atom exists. Let's assume that the atom sits at r equals 0, and so then what we have is that E equals E naught sine omega t. And I'm just going to ignore that little negative sign in the argument there, because I could just start my time at a different time to set the phase. So this is my electric field of the electromagnetic wave, and so then my perturbation Hamiltonian is going to be E naught sine omega t times q dotted with r. So h prime of t is equal to q E naught dot r sine omega t. Okay, so this is a very typical time-dependent Hamiltonian. So that's the time-dependent Hamiltonian that my atom sees when I turn on a laser. So this is coming out of the laser. Coming out of laser. I just want you to understand that. I mean, like, you turn on your laser, and so this is what you're doing to the atom. The atom is like, oh, I'm feeling this H prime. Okay, so that's what's happening. I just want that to be clear. Okay, and so now the question is, you know, now let's go back to this original question. So I'm sitting, my electron is sitting happily in some random level. It's a stationary state at time t less than 0. Then at time t equals 0, I hit it with my laser, and then some later time t greater than 0, I want to know where it is. I want to know what's the probability that it has transitioned from phi k to some new state, phi m. So what's the probability? Okay, so this is the problem that we're trying to solve. And so what we can do then is we'll do this. We'll assume that at t less than 0, then we have the Hamiltonian equals h naught, and we know all the eigenstates, h naught, phi n, e n, phi n. So these are just the atomic states. But then for t greater than 0, then we have h equals h naught, and here I can also say that psi of x t equals 0. We know which state we're in, right? We start in this kth state, but for t greater than 0, h equals h naught plus this perturbation, and then we want to know what is the probability to be in phi m. And I want you to understand what that even means. Basically, it's like if I turn on my laser and I then measure the energy of the electron in the atom, and I want to know where is it. So it's an experiment, you know. So I want to know. This is the results of an experiment. So I just want you to picture that, you know, because we're still working within the framework of quantum mechanics. I mean, so I turn on the laser, the Hamiltonian, and then I do a measurement, and I want to know what's the probability that my electron is in this nth state. And the reason why I'm emphasizing this is because really what you do is it's an ensemble. You know, the way to really visualize this is that, you know, the particle could be in any state, and so you have to do the experiment many times and then average the results, because it might be it's all probabilistic, because I might find that the atom is in different states for different experiments, because that's the nature of quantum mechanics. So, you know, it's an ensemble situation. Okay, So, all right, so how do we solve this problem? So first, what we're going to do is we're going to make an assumption. So normally, so the old way is that we would have psi of xt is equal to some constant Cn of phi n of x e to the negative I e n t over h bar, where Cn is the overlap of your wave function at time t equals 0. Okay, this is the old way that you remember from last semester. So this is how you would talk about the time dependence of the wave function. But now, but that's for h is equal to constant. But now we have this. We have h is equal to a function. You know, there's a time dependence here. And so we have to appreciate that this adds more complexity to the wave function. And so how it adds new time dependence. And so how can we take that into account? And so what we do is we can write the new wave function like this. Psi of xt is equal to the sum over n. But now we're going to have Cn of t phi n of x e to the negative I e n t over h bar. So we're going to make an assumption about the structure of the wave function. And what we're going to do is we're going to assume that this is a function of time. Okay, and so it still looks a lot like separation of variables, but we're adding this new degree of freedom, and so it's actually quite different from the old solution. You know, when you think about it, because the old solution just had a constant here, but we need to have here a function of time, and so the way to think about it is that because you have to appreciate in the old way there are no transitions. In the old way there are no transitions. The distribution is fixed. The distribution in energy is fixed. And in the new way we have transitions. Because you have to ask yourself, what does a transition even mean? This thing Cn of t, because this is the way you have to picture it in your mind. I have levels. These are the levels of phi 1, phi 2, phi 3, phi 4. These are the unperturbed states. And the way to think about it is that there's probability. There's a probability to be inside of each state, probability. And so the probability here is C1 squared, C2 squared, C3 squared, C4 squared, etc. And in the old way, these numbers were constants. And so even though the particle could have a probability to be in different states, that those probabilities never changed in time. And so that means that there were no transitions previously. But now what we have is that these are functions of time. And so basically what's happening, so this is really important. I want you to think of this is probability. And so you can think of this probability as a conserved quantity. So think of the probability as a conserved quantity. And that's true because we know that the integral of the probability is equal to what? What's the integral of probability?
1.
That's right. Or I could say, you know, the sum over n, the probability to be in En is also 1. Probability is conserved. There's a finite amount of it. And so when I write the wave function in this way with these coefficients in front of the eigenstates, those coefficients squared give me the probability to be in each of those eigenstates. And so you have to think of this as like stuff. You know, there's some stuff. And it's like, you can think of it as physical. So let's say that this guy has a big probability, a little probability, smaller. I want you to think of this as stuff, because I think this will help you to visualize what's happening. There's this finite probability, and you can think of it as a fluid. I think it's most useful to think of this as a probability fluid that can slosh around. And in the absence of a time-dependent perturbation, the probability is fixed. But when I turn on the time-dependent perturbation, the probability can ooze around. Probability can go from one level to another. And so a transition, when we're talking about a transition from, say, state phi1 to state phi2, then what that means is I have a lot of probability here at t equals 0, but then at some later time, phi1, phi2, some of that probability has shifted. The probability has moved. So the probability, think of the probability as flowing. The probability flows. And so what we want to do is so our job is to track the flow of probability. Track the flow of probability. And how do we track the flow of probability? By calculating, the way we do it is by calculating something. Let me remind you, the wave function as a function of time, we're now writing it like this. Cn of t, phi n of x, e to the negative I, e, n, t over h bar. How do we track the flow of probability? What do we have to calculate? What is the most important quantity?
Cn of t.
Yes. That's the most important thing, the Cn of t, because the probability to be in state phi m at time t is equal to this. P m of t is equal to this. We basically have to take the wave function psi x of t, and we have to project it onto that and square it, right? That's the probability to be in state m at some time t. But what is that? If we calculate that thing, if you calculate this, calculate it, and what do you get?
You just get the C factor and the phase factor with the exponential.
Well, let's actually, maybe we should just even do it. I mean, it's basically, first we calculate this, phi m psi x, psi xt. Let's just do it. And so it's going to be n c n of t, and we'll have this phi m phi n, right? E to the negative I e n of t over h bar, right? We're calculating it. What is this thing equal to?
Dirac delta. I mean, a Kronecker delta.
Right. And so that collapsed the wave function, or not the wave function, that collapses the sum. And so now it goes from a sum to this c m of t, e to the negative I e m t over h bar. But now let's square it. And so what happens to the phase factor when we square it?
It goes away and it's just Cm squared.
Exactly. And that is the probability. We just calculated it. That is the probability to be in state m at time t. So this is the most important thing. So this is what we want, okay? So I just want to emphasize that this is the most important thing. And and so we write the wave function in this new way. So you've actually never seen this before, unless you've taken this class before. Making that coefficient a factor of time is actually this big new thing. But I want you to see that it's actually a very natural, very normal thing. There's nothing weird about it, because it's just telling us the probability at time t to be in that state, the nth state. All right, so I just want to emphasize that this is a very natural way to write the wave function. Okay, but then the question becomes, can you guys hear me okay? Can you hear me?
Yeah, it's good now.
Okay, so so then how do we calculate this probability, Cm of t? How do we calculate it? Okay, so we have this thing. We know that the wave function is equal to this sum, phi n of x e to the negative I e n t over h bar. Then but how do we calculate this thing? How do we get it? So can someone tell me what to do?
Don't you do that thing, which in the E&M Griffiths book, it's called like Griffiths trig or something like that?
I don't
For
know. Oh, I think I know what you're talking about. No, yeah, no, there's something more that we have to do, actually. That won't work now, because this Cn of t is like, we don't know the functional form of the Cn of t. We don't know what it is. It's a function. It's a mystery function. Mystery function. How do we find this mystery function? It's not known. How do we calculate it? Can anyone guess?
Does it have to do with like the weight of the Cn at t equals 0?
Yes, it will. We will use that, definitely. But still, that's a boundary condition. So that's good. You're totally right. That's a boundary condition. But when we solve a problem in physics, typically we solve a differential equation, and after solving the differential equation, we then plug in the boundary condition, which is what you just said. So now I'm asking, what is the differential equation?
Would we plug in that psi into the Schrodinger equation and find some formula for Cn of t?
Yes, That's correct. That's exactly what we do. Good. That's perfect. That's exactly right. We plug into the Schrodinger equation. You know, if someone asks you a question in quantum mechanics, if you answer, use the Schrodinger equation, if you just randomly say that, you'll probably be correct like 7 out of 10 times. So if in doubt, just say, use the Schrodinger equation. So if I ask you a question, just say, how about the Schrodinger equation? You'll probably be right, because it almost always is the Schrodinger equation. Okay, so let's plug this into the Schrodinger equation. So let's do it. So here's the Schrodinger equation. The Schrodinger equation is h of t psi is equal to I h bar d dt psi. Let's plug into that formula. And so let's do it. So here it is. H is h naught plus h prime of t. And we know what h prime is. That's that electromagnetic wave thing that I derived. So we know that. And now we've got to plug in psi. Got to plug in psi. And we know what psi is. It's n. It's c n of t phi n, which are functions of position, e to negative I e n t over h bar. And then this is equal to negative h bar over I d dt of n c n of t phi n of x e to negative I e n of t over h bar. Okay, so that's what we do. And so now we just have to grind through some algebra. And when we grind through the algebra, the nice thing is that when this h naught hits this en, what does h naught turn into?
E sub n. What?
Exactly. That's exactly right. And so let's just do some of this algebra. So we're going to get, when the h naught hits it, it's going to be a sum over n, and it's going to be en, cn, phi n, e to negative I en, t over h bar. Then when the other guy hits it, it's going to be the sum over n h prime of t, cn, phi n, e to negative I en, t over h bar. So we're just grinding through the algebra. It's not hard. It's tedious, but it's not hard. Now I got to do the next one. And so this is going to hit it, but now I have to use product rule. Product rule, because it's a derivative of a product of two functions. Let's use product rule. It's not hard, it's just tedious. So product rule, negative h bar over I, sum over n, negative I over h bar, en, cn, phi n, e to negative I en, t over h bar. Okay, that's the first one. Now let's do the second one. Negative h bar over I. The second derivative, now I have to take the derivative with respect to cm, or cn, I'm sorry, I'm using n's. Cn of t dt by n e to negative I en t h bar. Let's get that in. Yeah, okay. That's our equation, but now let's do something, and let's notice that, let's notice something very cute, which is that two of these factors, well, you tell me. I mean, look at this factor and look at this factor. What can I say about these two factors? Someone tell me.
They're equal. They'll cancel out.
Yeah, they cancel. Yay. Yippee. Okay, and so now I get this equation. Negative h bar over I, sum over n, d cn dt, e to the negative I en t over h bar phi n is equal to the sum over n Cn e to the negative I En t over h bar h prime of t phi n. Okay, so you get this pretty horrific looking equation. Okay, it's it's actually a pretty complicated equation, but we can simplify it a little bit. Let's do a trick now. Let's do a math trick. And the math trick is this. Let's do this. This is the math trick. Let's left multiply by an arbitrary function. And you've seen this math trick before. Let's left multiply by phi m star. And I'm just going to do, we're just doing this all in one dimension. And then let's integrate. And when you do that, you see that what's going to happen is you're going to get negative h bar on the left over I, the sum of dCn dt e to negative I En t over h bar, and this will be an integral negative infinity to infinity phi m star of x phi n of x, and you guys know what that gives us, right? Right? Our old friend, what's this? What does this give us?
Kronecker delta.
Exactly. And so that collapses the sum. And then on this side, it's going to be Cn e to the negative I e n t over h bar, integral negative infinity to infinity phi m star h prime of t phi n dx. And this is actually a very special integral also. That should look, what does that look, what, that has a name. What is it, what type of, what do we call this quantity that I just, this one that the arrow is pointing at? What do we call that? That mathematical quantity?
Is it the mixing factor?
Say it again, what?
The mixing factor?
Yes, it is a mixing factor. That's correct. But it also is something else. It's like as a mathematical, like if you were looking, like if you were in a linear algebra class, what would you call that? I mean, what? It has another name too. You're right.
The matrix element?
Yeah, that's what I wanted to hear. It's a matrix element. And it's the matrix element connecting the M state and the N state. So we call this H prime of H prime M N T, because it's a matrix element, okay? And so this is, you know, this is row and this is column. I mean, it's literally a matrix element. So if we think of H prime as an operator, and it is, we can also think of it as a matrix, which you learned last semester. And so this is a matrix element. So taking all this together, now collapse this sum. Oops, this was not a sum over I, this was a sum over N. Now taking it all together, then we get this. dCm of t dt on the left, because the left side collapsed, and I can I can just do one line of algebra and I get this minus I over h bar, the sum over n of this matrix element h prime mn of t e to the negative I e n minus e m of t over h bar times c n of t. This is what we get. And you can see I simplified, I multiplied both sides, multiply both sides by e to the I ENT over H bar to do this, right? So that's how we get this final answer. There's, you know, one line of algebra. So this, this is our big result. This is our first big result from time-dependent perturbation theory. But we haven't really done the approximations yet. No approximations yet. And this, we've kind of run out of time, but this is telling us, this equation tells us, it tells us how to find Cm of t, which is the most important thing, because what we want to know is Pm of t, the probability to be in state m at time t, which is the square of Cm of t. And remember, this goes all the way back to this problem. You've probably already forgotten what we're even doing and why we're doing it. We're solving this problem, solving this. We have the atom at t less than 0. The electron is in one state. We turn on the laser at t equals 0. And then we want to know what's the probability to be in that state, phi m. And the probability is going to be this thing, Cm of t squared. So that's the problem we're trying to solve. And so now, look, we solved it. we did all that algebra, and we got it. We got this, but we got it sort of as a differential equation. So this equation that I now give 3 stars tells us how to solve it. But as you can, when you look at it, you realize it's actually a really hard equation to solve, because that's what we want. But notice it has the Cn's of t in it as well. So when you look at it, it looks like it might be impossible to solve, but actually we can solve it by using approximations. Then what we need next is going to be some approximations, and that will allow us to solve it. And that is really the essence of perturbation theory, are going to be those approximations. So we'll do that next time. Bye-bye. See you later.